Good day, Chem 1310. Today is a great day, and it's even a better day to learn about and continue our learning about balancing chemical reactions and the mole. Um, I have good news for you that I have a 1919 root beer. I've decided to let them, if they'd like, to be my official sponsor for this class. I haven't heard from them. I haven't reached out to them, but if they just want to spontaneously like start giving me money to drink a 1919 root beer during every class period, I'm totally open to that. Send it over and I'll get my legal department to look at it. But in the meantime, I'll be having this and we'll have our class like normal. So, balancing chemical reactions and the mole. So we're going to wrap up what we were talking about the other day with balancing chemical reactions. And we're going to look at this one right here. We got two examples. We have NaN3, and that goes on to yield. If you remember, that arrow usually indicates yield or is usually kind of referenced or referred to as yields, Na and N2. Okay, so first of all, I'm going to scribble this out, and then I'm going to write N2 down here. Um, you have to go atom by atom. I previously gave you the suggestion of looking at the hydrogens and oxygens last, but as you see in this next problem, we might actually have to do the opposite. But as a general rule, looking at the hydrogens and oxygens last is a great way to go. Now, in this problem, let's go ahead and look at our sodiums. There's one sodium on the reactant side or the left-hand side of the chemical reaction. And then lo and behold, there's one sodium on the product side. Okay, we're balanced there. Great. Then we've got our nitrogens. Okay, well, three nitrogens versus two nitrogens. Okay. Now we talked about this previously, and the thing that we talked about was that we can change the coefficients. So the number that comes before the symbol, but we can't change like the subscripts. Like this, I can't just be like, hey, it's three now. Can't do that. So what would we need to do? Well, I think an easy thing to do would just be, well, let's try by doubling this. Okay, so that gives us six nitrogens on the left side. And so we balance that by putting a 3 in front of the N2. So that gives us six nitrogens on each side of the reaction. Okay. But in the process of doing that, what happened to my sodiums? Well, I had two sodiums, or I have two sodiums, and then I have one sodium. Okay, so, oh boy, this changes things. Now I got to put a 2 there. Uh-oh. Oops. We're done. That's it. That's it. The end. Story. We solved it. Okay, so now let's go on to the next one. We've got Fe2O3, so that's an iron oxide, plus C yields Fe and CO2. Okay, so we've got iron oxide reacts with carbon to form CO2. Now, as you can see, the carbons are balanced already. That's great. The irons. Okay, well, you know what I think we want to do, just to kind of give the demonstration, we're going to go ahead and start with the irons and see where that gets us. And then we'll come back and do the oxygens. Okay, so if I start with the irons, I'm going to put a 2 in front of this. And I've already kind of hit a little bit of a wall because I put a 2 and that balanced my irons. So basically, this note of start with oxygen is just kind of, it doesn't save you a whole lot of time. It instead is just, or sorry, it saves you a very small amount of time because as soon as we balance the irons, we can't really go anywhere. It just drives us back to looking at this molecule and saying, okay, well, the irons are balanced, the carbons are balanced, so now I have to balance the oxygens. So with that said, that general rule of saving the oxygens and hydrogens for the end is still a pretty good idea. Now, let's go ahead and we'll leave that 2 in place, but now let's go and look at those oxygens. Okay, so we have this 3-to-2 ratio, which we actually saw that in the previous problem. So I think what I'll do is I'll put a 2 coefficient in front of this, and then I'll put a 3 coefficient in front of this. So that gives us 6 oxygens on the right-hand side. It gives us 6 oxygens on the left. It increases our ions to 4, but the good thing about iron is it's as a product, it's not a part of a compound. It's a free element. So all that I have to do is put a 4 here, and that's balanced. Then for carbon, balancing the carbon, all that I have to do is put a 3 there. So I'm done. And if I go back, I always like to think about my iron, Fe, C, and O. How many Fe do I have? 4. How many oxygen do I have? 6. How many carbons? 3. Now on the product side, 4 Fe, 3 carbon, 6 oxygens. So I'm balanced there. That's great. So this is good practice. And I think that, sticking with that general rule of oxygen, save the oxygens and the hydrogens for the end, that's going to be helpful. I mean, sometimes skipping that saves you a little bit of time, but as would be the case here, but it can kind of cause a little bit of chaos. Now, with that said, we've got this nice little activity, which what I'm going to do is I'm going to go ahead, make this an extra credit activity. I'm going to scribble this out. And what I'm going to do is say, let's see, I'll put this on the final exam. I'll make it an assignment that's worth 0 points, and it will be up to, let's see, complete at least one level of this game following the link here. The link's going to be in the the PowerPoint and the PDF. You know what? I'm going to do 1 point per level. So complete at least one level. That will get you 1 point. If you complete all 3 levels, submit an image of the screen with your score for each of those levels, and I'll give you 1 bonus point per level on your final exam.
I wrote it in, then it broke because I wanted to.
Okay. Do you want to say hi?
Yeah.
Come here. This is my son, Arlo. Say hi, everyone. Here you go, buddy. It's fixed. Say bye-bye, everybody.
Bye.
Say good luck on your test.
Look on your test.
There you go. Okay, so this is balancing chemical reactions. It's great. This is a good thing to practice. Now what we're going to do is move on to kind of like phase 2, the mole. This can be intimidating. And I'm not saying that like, oh, you should be intimidated, but I'm just saying that as like, if there's something that you want to maybe dedicate a little bit more time to and a little bit more practice to understanding, I think the mole is an important concept to really get a good grasp on. So a mole is, this is the way that it was described to me in my first chemistry class. 1 mole is just like a dozen. And I said, okay, cool. And I think that what's helpful is to, deconstruct that statement and deconstruct that idea. What is a dozen? A dozen is a word to represent a number. So a mole is a word to represent a number. Now, I apply that to my non-sponsor sponsor. If I go to the grocery store, I'm going to get a dozen 1919 root beers. And that's 12 of them. Okay. Now, 1 mole. If I went to the grocery store and said, I would like a mole of 1919 root beers, they would say, we don't have that many, sir. Because a mole, and we did this at the beginning of the semester, but I think it's always a good exercise to do, that 10 to the 23rd moves the decimal place in that direction 23 times. So that gives you 602.0000000000000000000000000000000. That's a mole. Now, typically, when you're talking about a mole of something, you're talking about something, well, you're talking about particles of something. So it's not really a crazy concept because you don't have a mole of dollar bills. You don't have a mole of 1919 root beers. So refreshing. So refreshing. Um, it's just such an astronomically large number that you have to be talking about something that is very, very small. Now, what does a mole look like? Well, there are moles, and there's, the American Chemical Society loves to kind of, to interest or to spark interest in like accessibility of chemistry. Here's a little mole. It's fun. And with that said, October 23rd is International Mole Day because October is month 10 on the 23rd. So 10/23. Now, what does a mole look like? Well, looking at all of these samples and thinking about a mole of something being 6.02 times 10 to the 23rd particles of that something. Are any of these a mole? Yes, every single one of these is a mole, at least. So we've got copper wiring here. This is a mole of copper atoms. Helium in a gaseous state as a balloon. This is a mole of helium atoms. Same thing with iron and sulfur and mercury. All of these are a mole of that element. Now, when we talk about moles, it's very common and important to talk about and think about the mass of a mole. So 1 dozen of something is 12 items. If you have 1 dozen, um, I think, yeah, let's think about if you have a dozen eggs, and I'm going to throw a little bit of a curveball at you. 12 eggs and 12 elephants. Okay. Do you have a dozen of each of those things? If you have 12 elephants, do you have a dozen elephants? Yeah, you do. If you have 12 eggs, do you have a dozen eggs? Yeah. Now, it's a little bit more common for people to be comfortable saying like a dozen eggs because that's the quantity that you typically are buying eggs in, unless you go to Costco in which you buy like 60 at a time, 5 dozen. Now, next up, what is the mass of 12 eggs? Maybe call it a pound and a half. What about a dozen elephants? Do they have different masses? Eggs, 12 eggs versus 12 elephants. Do they have different masses? They absolutely do. Okay. Now, with that in mind, when you think about a dozen eggs versus a dozen elephants and having different masses, I want you to think about that when you are evaluating and thinking about a mole of something as well. So if you have a mole of, actually, heck, let's go back. Do you think that all of these different substances, since it's a mole of each one of them, do you think that they have identical masses? They don't. If you have a dozen helium atoms, that's a balloon. That's in the balloon. And if you think about picking up a helium-filled balloon, well, chances are the weight of the balloon itself is probably greater than the weight of the gas inside. Now, if we think about iron, by contrast, well, if you had a dozen, or sorry, a mole of iron atoms, well, that's probably going to have a little bit of a greater mass than those helium atoms. Now, this is where we have the periodic table as a great reference point. So, what does a mole weigh? What is the mass of a mole? Well, that's something that you find on a periodic table. When we look at the periodic table, we have this number 6 for carbon. What does that 6 represent? Well, it's the atomic number. It's also the number of protons in a carbon atom. Okay. Now, the other number underneath the carbon or underneath C and carbon is 12.011. That is the mass of 1 mole of carbon. So if you had 6.02 times 10 to the 23rd carbon atoms, they would have a mass of 12.011 grams. which is what's displayed right here. Here is that charcoal, basically. That's 12.01 grams. Go ahead and take a wild guess as to how many carbon atoms are here. Well, it'd be 1 mole of carbon atoms, which is 6.02 times 10 to the 23rd carbon atoms. So refreshing. Now, sulfur. Okay, sulfur, what we got right here. If you have exactly 6.02 times 10 to the 23rd and exactly 1 mole of sulfur atoms, they're going to have a collective mass of approximately 32.1 grams. Copper is 63.5 grams. So the masses of these moles of these substances varies a little bit. Now, what is the molar mass of a compound? Okay. We previously talked about what makes up a compound. For instance, carbon dioxide, CO2. There's 2 oxygens for each carbon. Now, what we have here is, well, the total mass. If you have 1 mole of carbon atoms, that would be a mass of 12.011. If you have, if we think about CO2, and um, this is one, okay, so if we have 1 mole of CO2 molecules, then we have 1 mole of C atoms. Okay. We also have 2 moles of oxygen atoms. Now, this is something that's always kind of tough to wrap your mind around because we already seem like and feel like we're dealing with like massive quantities and crazy kind of quantities that's tough to wrap your mind around. But the way that I think is helpful to think about it is let's say that you had one car. Well, let's think about what that car is. Let's say it's a Buick LeSabre. That Buick LeSabre, I think everyone would agree that that car has 4 wheels. Okay. Those 4 wheels are parts of that car. That car also has one body, we'll just say. Now, those are 5 things that make up that one car. Okay. Now, let's say instead you have 12 cars. How many wheels do you have? You have a total of 48 wheels because you have to think about, okay, I've got 12 cars. One car has this many wheels, but I've got 12 of those. So that means I have 12 times as many of those wheels. Now, I think that's a helpful way to think about it because when you, and, sorry, I got to finish erasing this. When we see an example like this, 1 mole of CO2, I understand that a mole is a tough thing to wrap your mind around. So when you encounter a number like this, or a question like this, just do the following. If you have 1 dozen CO2 molecules, well, then you're going to have 1 dozen carbon atoms. You're also going to have 2 dozen oxygen atoms because each one of those CO2 molecules is made up of carbon and oxygen. So 1 mole of CO2, you have to account for, well, the mass of the carbon, 12.011. And then the mass of each of the oxygen, 1C, 2, I'm going to say times O, which is 2 times 15.999. I'm going to round that to 16 for all intents and purposes. So I'm going to say 2 times 16 is 32, and 1 times 12 is 12. So we're talking about 12 plus 32, which equals 44. Now, when we look at quantities or quantities, um, like this, 1.8 grams of H2O, 8 grams of Br2, zero point 0.1 moles of CuSO4, and zero point 0.1 moles of K2Cr2O7. How do we process this information? Well, in order to do this, we have to do what's known as dimensional analysis. And in dimensional analysis, you have a number, your starting quantity. So I'm going to say 1.8 grams of H2O. Got it? And then what I'm going to say is, well, I want to convert that into moles. So I have to go grams to moles. This is the known quantity, 1.8. And I have to have a conversion for H2O to get to moles. Do I have that conversion? Yeah, I do. Because the mass of hydrogen, and I'm just going to share that, like, we don't have to toggle to another window or anything like that. But the mass of 1 mole of hydrogen is 1. The mass of 2 moles of hydrogen would be 2. So I'm going to say 2 plus, and then the mass of oxygen. The mass of oxygen is 16. So 2 plus 16 is 18 grams. So 18 grams of H2O is 1 mole of H2O. Now, when you get to this sort of part of the problem, you have to think about, where am I going? Well, I'm going to moles. And when you look at the math, you can say, okay, well, grams of H2O are on the top and grams of H2O are on the bottom. So they would effectively cancel out. So what I'll do is I'll multiply everything on the top half of my dimensional analysis. So 1.8 times 1, that's 1.8. And then I'll say 1.8 divided by 18. So pulling this up on my phone, because that's where my calculator is, 1.8 divided by 18 is 0.1 moles of H2O.
Dad,
Yes, sir.
can Dad, can you fix it because this is because it's keep breaking apart, so I'm gonna put it in my room.
So if you have 1.8 grams of H2O, that's 0.1 moles of H2O. Now, 8 grams of Br2. Well, when you are trying to figure out how many moles of this there are, you have to, of course, compare that to the periodic table. Now, I'm going to save you watching me toggle back and forth. ptable.com, and bromine has a mass. Okay. If you look on the periodic table, you see Br is approximately, I'm going to round up to 80, 79.994. So 1 mole of Br is 80 grams. Okay. Now, if that's the mass of 1 mole of bromine, and bromine is Br, what's Br2? Well, there's 2 bromines. So this is a place where it gets kind of tricky. 1 mole Br2 is 160 grams. So we've got 8 grams, 160 grams, also of bromine, is 1 mole Br2. So 8 divided by 160. I'm going to plug that into my calculator. And whenever I do that, 8 divided by 160 is 0.05 moles of Br2. Okay. So that's how we take a mass to figure out moles. What about when we take moles to mass? Well, in that case, we want to set up our dimensional analysis where it is moles multiplied by grams over moles. So I'm going to say 0.1 moles of CuSO4. 1 mole CuSO4, well, Cu. Okay, so I'm going to have to go back and forth through the periodic table. Cu is 63.55. S is 32.06. O is 16, but there's 4 of them. So O, I'm going to say 4 times that is 64. So my total mass is, let's see, 64 plus 32.06 is 96.06. And then plus 63.55. That's going to get me 0.61. And then that would be 9 and 5, 159.61. So I'll take this and I'll say 0.1 mole CuSO4. 1 mole CuSO4. 159.61 grams. So we'll get 0.1 times 159.61 equals 15.961 grams. Now, for the next problem. Okay, so this would be our answer, 15.961. K2. Potassium is 39. So I'm going to say, I'm just going to do this one kind of quick. So K 39. Just going to use a nice round number there. I rounded it down. I'll round it down to 39.1 grams. I'm going to multiply that by 2 though. Cr is 51.996. Multiply that by 2. O is 16, but I got to multiply that by 7. So this is a pretty hefty number. So 39.1 times 2. That's 78.2. Plus, and you know what? I'm going to round that 51.996. I'm going to round that to 52. So I'm going to add that to 104. Plus 7 times 16 is 112. So I'm looking at a mass of 216 grams per mole. So 0.1 mole and then 1 mole of K2 Cr2O7. That's going to be 0.1 times 216 equals 21.6 grams per mole, or grams of that substance. So ultimately, this is central to understanding the concept of a mole. Being able to take a mass, which is what we did back here. We took masses of substances and determined the number of moles of that substance. Then taking a number of moles and converting that to a mass. Now, I think that it's fair to imagine, like, what's the next progression? Well, the next progression through this, which we're going to save until Monday, is taking the number of moles of a substance and converting to particles. So if you have 1 mole of a substance, you have 6.02 times 10 and 23rd of that something. If you have 2 moles of it, well, it's 2 times 6.02 times 10 and 23rd. What if you have 0.5 moles of that substance? Well, then you got 0.5 times 6.02 times 10 to the 23rd. Okay, so that's the next progression. And then it can kind of get a little bit complicated because you're adding levels and layers to this. So if we go back, we could go from grams of H2O to number of moles of H2O, and from number of moles of H2O to number of particles of H2O. Now, all of that to say, this is a process. This is something that gets progressively more challenging, but that's not to say it gets more impossible, or it does get more difficult. So I'm not going to say, oh, it doesn't get more difficult, but think about it as it's fundamentals. You have from here, what we've done is we've looked at mass to moles. That's a tool. Can you convert from number of grams of something to the number of moles of it? Yes, we did that right here. What about could we go the opposite way? Moles to mass. Yes, we did that right here. So could we in the future go from mass to moles? Done. And then moles to particles? Done. Yes. Do these numbers get a little bit complicated because of scientific notation? They do. But that's not to say that it is impossible. We're going to save that for next week. In the meantime, though, I hope you have a great weekend. I'm going to stop my share right now. And if you've got any questions about anything, please contact me so I can help you out. All right, everybody, have a good one.